Now we are going to investigate the washer method, which is different than the disk method, and I'm going to explain why. We're also going to be rotating about a horizontal line. In the future, we'll do a vertical line. Now, the washer method is necessary when there is a gap between the region that you are rotating and the axis of rotation. So when that gap exists, you will be using the washer method. There's no gap, as we've seen previously, you use the disk method. Anyway, we'll see that when we go ahead and graph this particular region. Example 1, find the volume of the wedding band, and we'll talk about why it's a wedding band when we visualize it, obtained by rotating the region between the graphs of f of x equals x squared plus 2 and g of x equals 4 minus x squared. We're going to be rotating this region bounded by these two curves around the line y equals negative 3. Again, for the initial step, or step 0 as I like to call it, we will get y by itself. We have to get y by itself when rotating about a horizontal line. Okay, and when you get y by itself, both of these equations should be in terms of x. You have f of x equals x squared plus 2 and g of x equals 4 minus x squared. That has to be the case when you're rotating about a horizontal line, because your limits are going to be in terms of x for your interval. Next step is to draw the Cartesian plane, which goes along with the step afterwards. Once you draw the plane, then you want to sketch the region in question on the plane. So here I've sketched f of x equals x squared plus 2, and g of x equals, already forgot what it was, 4 minus x squared. Okay, so this one down here is actually f of x. All right, and then g of x is the one on the top. Okay, so, how do we know where they cross? Well, if you look at where they cross, here and here, they cross at -1 and 1, and that's because, and actually those are x values, by the way, and you obtain that by simply setting these equations equal to each other and solving, and you will basically get 2x squared equals 2, and you'll solve for x, and you'll get x equals plus or minus 1. And so, but that just goes back to sketching graphs and figuring out where they cross. Anyway, you want to do that first, and you also want to sketch your axis of rotation, which is at y equals -3. Right off the bat, you see that you will need to use the washer method because the region that you're rotating is way up here, right? And you want to rotate way down here. So there is a huge gap between the region and the axis of rotation. That's when we know we use the washer method instead of the disk method. The washers are going to end up looking like this. There will be a hole in the middle, and that's why it's called the washer method. If you've ever done any construction or any kind of handy home improvement, you might have used a washer to secure a nut or a bolt. And so there is a hole here, much like a donut. So you can almost call this the donut method when there's a gap. Okay, the next step is to sketch the lines of intersection of the washers and the region. Okay, so again, we have our f of x down here, which is x squared plus 2, and we have our g of x right above it. We'll just do it green this time, which is 4 minus x squared. As we can see, the cross sections in pink are way, they are way outside of where our axis of rotation is. And because of that, it will form a big hole between our region and our axis of rotation if we rotate this all the way around. Now that leads us to want to show what this three-dimensional shape looks like before we go and solve it, so you can have a conceptual understanding of what this looks like. So once again, I'm going to be using this app, which was created by Tom Brzezinski using GeoGebra. Here is our region up here. I had to zoom out so that we could see what this looks like when we rotate it. We're rotating f and g, which are up here on this line y equals -3. So you can see that when you rotate this region all the way around, it forms something like a donut. Okay, and if we rotate this, looks more like a wedding ring, right? Because it's so thin on the edges. So you can imagine why this is called the washer method, because there's this huge hole right here in the middle. Okay. With the disk method, there is not a gap, and so you end up getting a solid shape with no hole in it. So this looks like a wedding band. And with that being said, let's go ahead and find the volume of this wedding band. And of course, we will have to subtract this inside area since it's a hole. So here's how it works. First of all, you want to figure out the next step 5, determine the function closest to the axis of rotation. And in this case, it's going to be our f of x equals x squared plus 2. It is closest to our line y equals -3. For step 6, you want to determine the function farthest away from the axis of rotation, and there's really only other choice, and it's this green function g of x equals 4 minus x squared. I like to call the one furthest away my big F, and the one closest I like to call C. You can do whichever one you like. Doesn't really matter. Actually, I like to call that big R. A big R, not a big F. So the one further from the axis of rotation we will call big R. As it's further away, I like to call it big R, and the one closer we will call little r. Let me go ahead and fix that real quick. All right. What we're going to do now is determine our little radius. If the region being rotated is above the axis of rotation, then r equals c minus a. And the reason we want to choose c is because it's closest, so we will call this function c. The function furthest away, for furthest, we will call f. Alright, so the next step is to determine your little radius. Now for conceptual reasons, let's look back at our three-dimensional rendering. The little radius would be from the middle of this ring to the function closest to it. And so from the axis of rotation to the closest function will be your little radius. Then we will find the big radius, which will go from the middle to the outside of the band. So the little radius then will be your closest function minus a, and that's if the rotated region is above the axis of rotation. As you can see, our region here is indeed above the axis of rotation. To find our little radius, which I will mark here in purple, this little radius right here will just be our closest function c minus our axis of rotation a. You can see that if it were the other way around, it'd be a minus c. So anyways, for right now it's above, so we're going to do c minus a, and that will give us a formula which will give us the any one of these smaller radiuses. So in this case, it's going to be x squared plus 2, which is our closest function f, minus our axis of rotation -3. 2 minus -3 is plus 5. So for right now, little radius is going to be x squared plus 5. And again, that will give us the length of any of these little radiuses, no matter how far along the graph we are, all the way up to 1. Okay. Now we want to figure out a formula for the big radius, and it's just going to be the function furthest away minus a. And again, that's if the region is above the axis of rotation. For the next example, we will look at what happens when it's below. So this will be f minus a, 4 minus x squared minus -3, which simplifies to 7 minus x squared. And I will just use the color orange for that. So our big radius is going to be 7 minus x squared. The way to visualize it on here would be from going from, say, all the way to the top furthest function all the way down to the axis of rotation will be our big radius. And again, if we look at three-dimensional rendering, that would be like going all the way from the outside of this band all the way to the center, which is that y equals -3. Now, why are we doing that? It's because we still have a bunch of circles that are generating this wedding band. We have an outer circle, which we just found to be our big R, and that is the larger radius, and the inner circle is determined by the smaller radius, the closest function minus the axis of rotation. So if we found big R squared minus little r squared, it would give a miniature washer, basically. And if we added up all the areas of those washers, we would get the volume of this ring, which is why it's called the washer method. And so now that we found little r and big R, we will next draw our washer and label the little radius and the big radius. So as you can see, our big radius is going to be this right here, which I'll try to do. That is our big radius. Our little radius will be right here, and it's represented by x squared plus 5. You can see that if you took the area of this circle and subtracted the area of this circle, you'll get the area of the washer. We will use that when we go to integrate our function, because again, if you do a bunch of these washers rotated all the way around, you will get the volume of that ring. And again, we can slide this around and see what that looks like. See if I can make this big here. And you can see that this wedding band is nothing but a bunch of those rings put together. Infinitely many of those washers form the ring. Okay. Going back, now that we've done that, the step 10 is going to be determine limits of integration. It's the range of the washer cross sections. Basically, again, those ranges are in terms of x. And if you zoom back to where I originally drew this, they range from -1 to 1. So those washers are going to go all the way from -1 to 1, as we notated here. And again, it has to be in terms of x when you're rotating it around a horizontal line. Everything has to be in terms of x. That will be a range from x equals -1 to x equals 1. Okay, now we're going to set up our integral. And again, to find the area of any of those washers, it's just pi big R squared minus pi little r squared. Now what you can do is you can pull a pi out and put it in front of the integral to use the constant multiple rule. Inside the integral, you're left with big R squared minus little r squared. So it's almost like a disk method, right? Instead of pi r squared, you have two r's inside, big R squared minus little r squared. Just don't forget the pi. It's important because that's part of the area of the two circles. So we're going to be going from -1 to 1. Don't forget your pi. Big R squared is 7 minus x squared. So basically, let me use orange here to be consistent. Basically what we're doing here is replacing big R with 7 minus x squared. And yes, it is still being squared, so we put it on parentheses. And then for little r squared, we replace it with x squared plus 5. Putting in parentheses, subtracting it, and squaring it. Don't forget dx. Now we want to make this easy to integrate, so this is just foiling these. I'm not going to spend a lot of time explaining that. But in calculus by now, you know how to foil a binomial or square it. You will do some simplification and combine some like terms. I pulled 24 out, and now we have a simple integral 24 pi times the integral from -1 to 1 of 1 minus x squared dx. You can use the reverse power rule to now find the definite integral. So now what I'm going to do for the final step is evaluate the definite integral. And antiderivative of 1 is x. Antiderivative of x squared is 1/3 x cubed. Subtracting, plug in 1 for my upper limit, and plug in -1 for my lower. Making sure to put my lower limit around parentheses so I know to distribute my negative. And it's all said and done. Doing some simple algebra and adding and subtracting numbers. And it with 4/3 in the bracket, multiplying it by my original 24 pi. And lo and behold, we get the total volume. We get 32 pi, which, if you think about that, that's about 100. 32 times 3.14. Okay, it's not exactly 100, but I'm just going to put around 100. And those are going to be units cubed. So basically, what that means is the volume of this wedding band, as we like to call it, is around 100 cubic units. Pretty interesting. Why so much? Well, it's because it's a large ring. It has a big outer radius. Okay. So there you go. There's the volume of our wedding band when using the washer method. If you have any other questions about these steps and how to get to the answer, let me know.